Graphs are generally used to represent the information of certain equations from specific cases. In physics, there are three types of graphs that are going to be useful to analyze the constant acceleration. Position time graphs are related to where the object stands at what time. Its slope represents velocity since the formula is velocity equal to displacement over time. When the segment has a straight line, this means that the velocity is constant. And when the slope is negative, it means that the velocity is also gonna be negative. When the line is not in a straight line and it's a curved line, it means that the velocity is changing, so therefore there will be an acceleration. Velocity time graphs are not related to the position of an object, unlike position time graphs. They represent how fast an object is moving, so its slope represents the acceleration of the object, since acceleration is equal to velocity over time. When the slope is positive, it means that the object is increasing its velocity in a positive direction. And when it is negative, it means that the object is increasing its velocity in a negative direction. So when we want to determine where does the object stands, we need to use the area of the shape that the slope creates. Acceleration time graphs measure how fast is the acceleration of the objects. Therefore, when we have three different objects that move at different velocities but constant velocities, they're gonna have the same acceleration of 0 meters per second squared. The slope of the graph is called jerk or jolt, with the formula of jerk is equal to acceleration over time. As in velocity time graphs, to find the change in velocity of an object, we calculate the area of the shape that the slope creates.
So let's talk about the cases. In the first case, where a equals to 0 and the initial values for velocity and position are random, the position time graph presents a straight diagonal line. This is due to a constant velocity, which is only possible because a equals to 0, causing to be no changes in velocity. The velocity time graph presents a straight horizontal line, with its y-intercept being the initial velocity. This is caused because of the same reason that the last graph didn't suffer changes, because its lack of acceleration. No acceleration means a constant velocity, which is shown in the graph. The acceleration time graph presents another straight horizontal line, though this one has its y-intercept at 0. This graph's reason of being is a bit more obvious. A equals to 0, and it remains like that for the entire simulation. In the second case, where all three variables are random, the position time graph now does not present a straight diagonal line, but a more curved one that as time passes it gets steeper. This is because now there is a value for acceleration, which means velocity is constantly changing. The velocity time graph now is not a straight horizontal line, but a straight diagonal one. This is because now that acceleration has a value, velocity is at a constant increase. The acceleration time graph now presents another straight line, though its y-intercept is now at 2 and not at 0. In the third case, where also all three variables are random, for the position time graph the properties remain the same than in the last one, though it can be stated that this graph is less steeper than the first one. This is because the acceleration in this case is lower than the one used in the second case. The velocity time graph has also the same properties from the last case, and as the previous graph, the steep from this one is less than from the last case. Again, because the acceleration is lower in this case than the one used in the second case. The acceleration time graph presents a straight horizontal line with its y-intercept at 1. So now let's find the velocity and the position if time is equal to 8 seconds. So in case 1, what we need to do first is to write down the data we already know. For instance, we know that velocity is at a constant of 10 meters per second and the time is 8 seconds. And what we don't know is the distance or final position of the car. We also know that distance is equal to velocity times time. So knowing that formula, what we'll need to do now is to rewrite the formula, but with the variables changed for the data we already know. So we write down d equals to 10 times 8. And then we solve 10 times 8, which is equal to 80. But then we also have to take into account that the initial position is equal to 15 meters. So what we do next is to add those initial 15 meters to our current 80 meters, which gives us an equal of 95 meters, and that is our final position. So for case 2, we're gonna follow the same methodology that we followed in case 1. Though this case does include acceleration, which means that it'll be more complex than the last one. And well, as the first case, we are going to write our data down, leaving just the final position and final velocity as unknown. Then what we're going to do is write a formula to either find velocity or final position. I decided to find first final velocity because for a formula to find final position, we must know velocity. So once we have our formula written down, what we must do now is to replace our variables with our already known values. And then we start solving until we get our final answer, which is 21 meters per second. Now our only missing variable is final position, which we're going to find right now. So we write down our formula, which includes velocity as mentioned previously, and we, as previously, are going to replace our variables with our values. Once we've done this, it's pretty straightforward. We just have to, as previously, start solving to get our final answer, which is 114 meters. So now we know our final position, which is 114 meters, and our final velocity, which is 21 meters per second, if time is 8 seconds. So finally, in our last case, we also need to find final velocity and final position, and we're going to follow the previous method. So what we do now is to write down our data, and once we've done this, we're going to follow the previous formulas. And as before, I'm going to start with velocity because I'm going to use velocity to find out what final position is later. Once we've written our formula, we can now replace the values and start solving to get our final answer, which is 20 meters per second. And once we've known our velocity, we can now find our final position. Once we've written our formula, we can replace the variables with our known values. And again, we just solve for the final answer, which is 124 meters. So now we know our two missing variables, which are final position equals 124 meters and final velocity equal 20 meters per second.